All right, today what we're going to start talking about is we're going to start talking about the isotopes. And again, if you remember where we left off with that current atomic model of what the atom looks like. Again, we had our protons and our neutrons in that nucleus, and we had the electrons floating around the outside of that nucleus in the electron cloud. Henry Moseley, he started looking at the atom a little bit actually after Rutherford, and as he was looking at that atom, he noticed that through an X-ray experiment that nucleus had a unique integral positive charge. And again, when he was looking inside and at that nucleus, again, we remember at that time that we only had the protons in there. Again, he noticed that there was this integral positive charge. Now that integral positive charge is now going to be referred to as the atomic number. It is the number of protons in the nucleus of an atom. And the thing about the protons in the nucleus of an atom is this determines the chemical identity of the element. Now, when you look at a periodic table, the atomic number is always going to be the whole number on the periodic table. Again, there's going to be a lot of information when you look at my periodic table, but I'm just giving you a generic one here of aluminum. And when we look at aluminum, we see the 13 here, and what that 13 tells me is we have 13 protons in that nucleus of an aluminum atom. Or on the other hand, if you were told that something has 13 protons and they asked you what it was, go to the periodic table, find element number 13, and again, 13 corresponds to aluminum. Now, because an atom is electrically neutral, now this is going to be for this chapter only, but because an atom is electrically neutral, the atomic number is also going to represent the number of electrons. So for example, when we were just talking about aluminum, when we looked it up, we said 13 protons. So for right now, what we're going to say is it will also have 13 electrons. Now again, J.J. Thomson did quite a bit with the atom. Again, he was the individual that found the electron. He was also the individual that came back and found the proton also. But while he was working with neon, J.J. Thomson found what appeared to be two different kinds of neon atoms. They were alike chemically, but they had difference in masses. Okay, so again, remember John Dalton, one of his statements was all atoms of the same element are alike. Well, again, J.J. Thomson knew that, but while working with neon, there were different masses in the nucleus of those atoms. And what this is now today is going to be an isotope. An isotope is just going to be an element with the same number of protons, but a different number of neutrons. Okay, so again, John Dalton would have said there's one and only one kind of neon, but J.J. Thomson, while he was working, found different neons. And the difference comes from the number of neutrons. The number of protons has to stay the same because remember, that's the chemical identity of that element. Each isotope is just going to be represented by a nuclide or as a nuclide. What is a nuclide? It is a particular isotope of an element. So if we're talking about this isotope, again, it's going to have a certain nuclide notation. If we're talking about a different neon, it's going to have a different nuclide notation. But again, a nuclide is just specifically talking about a certain isotope for an element. For example, neon 20 and neon 21. Those were the two particular kinds of neons that J.J. Thomson was looking at. So this neon 20 and neon 21, this is going to be what is referred to as nuclide notation. So again, this neon 20 and neon 21, this is going to be referred to as nuclide notation. The 20 and 21, that just represents the total number of particles in the nucleus of an atom. Now again, remember, atomic number, that's just the protons, but the 20 and 21, that's going to tell you the total number of particles in that nucleus. Isotopic notation for the following two forms of neon would look like this. So we have isotopic notation, and the one earlier that I just showed you was nuclide notation. Now, when we look at isotopic notation, what is specific about isotopic notation is this. First thing that we do is we go ahead and represent each by its symbol. And then the next thing you do is you go ahead and put the nuclide that we're talking about. So for example, number 20 is going to go there. And then the other thing that you do is you go ahead and put the atomic number down here. So the complete mass or the nuclide is going to be written in the upper left-hand corner, and then the atomic number is going to be located in the lower left-hand corner. If we were to look at the other one, neon 21, again, symbol Ne, and now this one, its nuclide is number 21, and again, the atomic number being 10. So again, in isotopic notation, we have this. Now, when you read through your book is also going to refer to isotopic notation, but they're going to call it symbolic notation. So we have nuclide notation, which is shown up here with the neon 20 and neon 21. We have isotopic or symbolic notation down here, where you have your mass number or mass up here, and then the 10, and the atomic number is going to be located at the bottom. Now again, whether I was talking isotopic notation or nuclide notation, again, you saw the 20 and 21. Okay, again in each form. That 20 and 21, that is just going to be referred to as the mass number. That is the total number of protons and neutrons in the nucleus of an atom. So if we wanted to find just the number of neutrons, what we're going to do is we're going to take everything that's inside the nucleus and subtract away the atomic number. So again, we're going to take mass number and we're going to subtract away the atomic number. So if I were to look at those two forms of neon, neon 20 and 21, first thing I do is I go to the periodic table. When I go to the periodic table, again, you're going to notice that it says the atomic number is going to be number 10. So again, because it's neon, or both of them are neon, again, I can put 10 protons on each one. Now, again, if you remember back to one of the previous slides, it said because an atom is electrically neutral, this is also going to be the number of electrons. So again, whether we're talking neon 20 or neon 21, it's going to have 10 electrons also. So 10 protons, 10 electrons. Now, to find the number of neutrons, the number of neutrons is just going to be, it said to take the mass number, okay, and on this one here, it's number 20, okay, so that's its mass number. We're going to subtract away 10, and when you take 20 minus 10, you end up with 10 neutrons also. Over here on this one, the mass number is 21. Again, I'm going to subtract away the 10, and when I subtract away 10, we're going to have 11 neutrons left for neon 21. Now, both of them have 10 protons, both of them have 10 electrons, but what makes it an isotope is the number of neutrons is different. For neon 20, it only has 10 neutrons. For neon 21, it has 11 neutrons. Now, knowing that there are different isotopes of an element, scientists calculate the average of all of those isotopes together. And that's going to be the atomic mass. That's the average mass of all of the isotopes of a particular element. So again, when you look at that periodic table, you're going to notice that there's a decimal number. And that decimal number comes from an average of all of the isotopes together. And again, what they are is they are averaged by their abundance. When you glance at the periodic table, you can quickly identify which isotope is going to be the most abundant. When I go ahead and I look at aluminum again, here is the atomic number, and this is going to be the atomic mass. Now, one thing to tell you is when I look at aluminum, aluminum has 22 different isotopes, ranging all the way down to aluminum 21 and going up to, I think it's all the way up to aluminum 42. But again, those are the different nuclides, specific isotopes. But when I average all 22 isotopes together, its average mass comes up to be 26.98. But if I go ahead and look at this and take this number right here, 26.98, round it to the nearest whole number, and you get 27. What that's saying is the most abundant isotope of aluminum is going to be aluminum 27. So let's go ahead and look at a couple of examples on how to calculate average atomic masses. It says calculate the atomic mass of an element that has an isotope with a mass of 6.015 AMUs, or atomic mass units, and an abundance of 7.5%. And it says the other isotope has a mass of 7.016 AMUs, or atomic mass units. Now again, you notice here that we're talking about percentages, and percentages are always out of 100. So when I look at this, again, that 7.5% is going to go with the 6.015. Well, again, that leaves the rest of the percentage to be with the 7.016. And again, when you go ahead and take 100 and subtract away 7.5, you're going to find out that the rest of it, or 92.5%, is going to be 7.016. Now here's the thing. Anytime you are dealing with percentages, go ahead and convert it into its decimal form. So what you'll do is you'll take 6.015, you'll multiply it by 0.075. We'll take 7.016, we'll multiply it by 0.925. We'll add those two numbers together, and when I do that, you're going to find out that the average is 6.94. And when you look here, 6.94, it's closer to 7. There's a greater abundance of this isotope here, and again, it pushes that average closer to the greatest abundance. Now again, this is one that was dealing with percentages. Let's look at one that doesn't have percentages. Maybe this one is total sample size. It says here, what is the atomic mass if out of every 169 particles, 16 have a mass of 27.5, 34 have a mass of 28.1, and 119 have a mass of 29.7. So again, what we'll do on this one is we'll take 16 times 27.5. We'll add it to 34 times 28.1. We'll add that to 119 multiplied by 29.7. Now, because this one is by sample size, we have to do an extra step. We have to divide it by the total population. And again, the nice thing about the other one was percentages are out of 100. And when you convert 100 into decimal form, that's just 1. And anytime you divide something by 1, well, it's just going to be itself. But when you have sample size, you still do the same thing up here. But the final step is just going to be dividing by however many total particles there were. In this case, it says there were 169 particles. When you do that, you'll get 29.2. And again, when you look, 27.5, 28.1, 29.7, that 29.2 is closer to the 29.7 because, again, it has the greater abundance.